Let's start talking about the parts of chapter 6.8 that are important in homework part 2. Let's think back to some stuff we discovered in kind of part 1. The integral from 1 to infinity of 1 over x squared converged. So that's drawn in blue here. The area under this blue curve from 1 on to infinity was a finite value. We also saw that the integral of 1 over root x, which is also 1 over x to the 0.5, that diverged, and that's shown in the red line here. So the area under that red line all the way out to infinity was infinite. So what do we think about, can we come up with a rule about when the power is this, then the integral converges or diverges? One interesting thing to think about here, it's kind of strange to see that 1 over x squared is smaller than 1 over x. I've drawn 1 over x with the black line. But you have to remember these values are less than 1, and if you square something less than 1, it gets even smaller, like 0.5 squared is 0.25. So that's why we're seeing these, this 1 over x squared is actually smaller than 1 over x, even though usually we think of squaring as making things bigger. And also, taking the square root of things less than 1 actually makes them bigger. The square root of 0.5 is 0.707-ish, right? So that's why we're seeing that. So do you have a guess as to, like, when the power is this, then the integral converges, and when the power is this, then the integral diverges? Just based on this example, we might say if you have the integral 1 to infinity 1 over x to the p dx, we might say that converges if and diverges if what? We don't have a lot of evidence here, but x equals 1 seems like it would be kind of important, so we'll just temporarily say that this converges, like when p equals 2, this integral converged. So we'll say if p is greater than 1 and diverges if p is less than 1, like 0.5. So that leaves a few questions. Is this guess even right? And the textbook shows that it is. You can go read their, it's not very complicated, but they already wrote it out, so you might as well read it there. The other big question, can you think of it? What if p equals 1? I didn't put a greater than or equal to, greater than or equal to here. So let's think about that. If p equals 1, so we'd have the integral 1 to infinity 1 over x to the 1 dx. And what's the integral of 1 over x? It's just log x. We actually don't have to be careful about absolute values here because all the x's are positive, but it's just kind of habit at this point. So I'm kind of being lazy here and saying we'll like plug in infinity. So what do we get here? Log of infinity minus log of 1. And what is log of infinity? Well, we have to think about the log graph. That's why it was on our organizer at the start of the chapter. And that is going to infinity, very slowly, but it is going to infinity. So we're getting here infinity, log of 1 is 0. That's not going to change much. So that integral is infinity. So this integral 1 to infinity 1 over x dx diverges. And so where should we put equals here? Well, if p equals 1, then the integral diverges. So we'll put an equals sign there. One quick thing here, we're starting this at 1 just to avoid putting a 0 there, because then we'd have a vertical asymptote as well. You could start it at 2, you could start it at 10, you could start it at 5 billion, you could start it at 0.1 or 0.01, just as long as it's not 0. And any finite change you make isn't going to affect whether the overall integral all the way to infinity increases or diverges or converges. So this is called the p-test. This concept right here is called the p-test, and I actually give it a more specific name because we're talking about integrating to infinity horizontally. I call this the horizontal p-test. So that is a really good way of thinking about a bunch of integrals that pop up, and even ones that aren't so simple we can kind of informally reduce to a p-test. So that should be a big tool in your toolbox. Now you're probably wondering, well, if that's the horizontal p-test, what else is there? There must be a vertical p-test. So go ahead and think about what we just said about all this integrating to zero to infinity horizontally. See if you can write out what the vertical p-test might be for yourself. We're probably worried about vertical asymptotes, right? So it would be the integral from 0 to 1 over x to the p dx, which is this part, this vertical asymptote part. Let's think about the ordering of these blue curves, the blue, the black, and the red. Here the y values are above 1, so squaring 1 over x gives us 1 over x squared and makes the number bigger, so we're moving up from the black curve to the blue curve, and taking square roots of things above 1 makes them smaller, so we'd be moving from the black curve down vertically to the red curve. So I think our intuition works a little bit better there than it does over here about squaring and square rooting. At least mine does. So what would you guess about this vertical p-test? Well, we already did these integrals in a previous video. So we can say the integral converges if and diverges if. And what would you say the conditions are there? Well, we saw that when the power was square root, the integral converged, and that was kind of underneath the other two. So if the power was less than 1, then the integral converged. If the power was greater than 1, then the integral diverged. Let's compare that to the horizontal p-test. So horizontal integral converges if p is greater than 1. Vertical p-test, the integral converges if the p is less than 1. So that's a big difference why we want to have different names for the two tests, because the greater than less than is different. What about if p equals 1? So go do this integral for p equals 1 and see what you get. So we go 0 to 1 over x dx would give us log of absolute value of x. Again, all the x's are positive. We don't really need to worry about the infinite, about the absolute values. So this would give us log of 1 minus log of 0, which we'll kind of put quotes around. Log of 1 is 0. Log of 0, let's think about what log looks like. Log of 0 is negative infinity. So altogether this would be positive infinity, so the integral diverges. So where do we put the equal sign in the vertical p-test here? The integral diverges if p is equal to 1, so we put it there. So it's an interesting symmetry, non-symmetry between the horizontal and vertical p-test. The converges versus diverges, you flip the greater than or equal to, greater than or less than, but p equals 1 diverges in both cases. So the equals goes on diverge in both of them. Other than that, you flip the inequality. So that's the horizontal and vertical p-test. Let's sneak in one more quick question. How about the integral 1 to infinity e to the negative 2x dx? If you graph that, it looks like that. So can we use a p-test on that? Which p-test would it be, and can we actually use it? It would be the horizontal p-test because we're integrating to infinity. What would you say p would be there? P equals 2, negative 2. Well, the answer is p does not equal anything because here we have x in the exponent rather than in the base. So notice in the p-test here, p is a constant in the exponent, but here the exponent is not constant. So we can't use the p-test at all. We can't say p equals 2, p equals negative 2, because the base is constant rather than having an x in it. So it's just a completely different function form. It's an exponential function rather than a power function. So the base is constant here. And the power is a variable. So p-tests are great, but you can't use them in every situation. We would have to go back and actually do this integration. And while we're integrating exponential decay, and the exponential decay is happening twice as fast as it did in our very first example. So what do you think is going to happen? I'll let you figure that out.